Okay, good afternoon, everyone. So we have the perfect speaker for after lunch talk, and I hope you guys are all awake because he's going to present some interesting things on superconducting van der Waals devices for quantum tech.
Okay, thank you, Devala. I'm happy to be here, part of this meeting, and I'm going to talk about some sort of more of engineering into the title of this conference, which is engineering of some 2D devices. So let me add that to this meeting. So I'm going to tell you about 2D materials, van der Waals, Josephson junctions. So there are two sub-stories in this talk, but the common thread running through this talk is Josephson junctions and what you can do with it, some sort of interesting technological implications. I'll try to make it clear. And I'm happy if there's a burning question, if you interrupt, I'm happy to stop and clarify. So I gratefully acknowledge the funding for our research from Department of Atomic Energy and Department of Science and Technology, which makes the work possible. So at the outset, I want to sort of say that I'm grateful to have some outstanding students and collaborators which make this work possible. Of course, I'm giving the talk, but the hardcore important work is done by people. These are my students on a hike that we went a couple of years ago. You don't see here, there are these two guys who did a lot of the work. Sanat is a PhD student now at Columbia, and Joydeep, who's another PhD student, finishing up and headed to Princeton. These are sort of the collaborators for different parts. So the first part of my work will talk about Josephson junctions using high TC superconductors. And we collaborate with my colleague Tamilvel, who's a expert crystal grower, particularly makes outstanding high TC crystals that have been central to our work. For theory, we collaborated with Felix von Oppen at Free University of Berlin. The second part of the work is Josephson junctions using graphene, which is proximatizing, superconductor proximatizing a graphene channel. So it basically becomes a tunable Josephson junction led by Joydeep. We collaborated with my colleague RVJ, and we, like many of the others here, we get some outstanding HBN from NIMS. Okay, so let me get started. This is my rough outline because there are a lot of students. And in general, I like to start with a pedagogical sort of component. So I'm going to talk about Josephson junctions. So I'm going to try to make a case for why they're interesting, why it's worth your while to think about them if you haven't been thinking about them already. What makes them interesting? How they are realized. That's stuff that I'll talk about to get us going. Then I'll talk about a particular experiment. The central result of that work is a realization of a Josephson diode. So this sounds like a little bit of jargon, but it's a diode, a non-reciprocal device, which is based on the Josephson physics. Then in the second part, I'll talk about the second kind of Josephson junction using graphene, which you can actually show. We have already shown it to work as a very nice quantum noise limited amplifier. Okay, that same architecture can also make extremely sensitive sensor. I'll show you an example of a bolometer, which can sense, sort of one of the best bolometers that are out there. And I'll end with what's next that is on our sort of to-do list in a sort of a big picture way. I won't go into specifics. Okay, so what is a Josephson junction? So we all sort of know at a zeroth level, a superconductor, independent of the pairing mechanism, has this very interesting pairing up of electrons, and the paired electrons, the Cooper pairs, kind of manifest the macroscopic sort of wave function of the superconductor. Okay, and many of the central sort of observable properties of the superconductor emanate from the simple idea that there is this macroscopic coherence throughout the superconductor. Now, what a Josephson junction is basically a superconductor interrupted in the original version by an insulator separated by an insulator and a superconductor on either side. And if the insulator is thin enough, what you have is basically the complex many-body wave function of the two superconductors has this phase which is sort of characterizes the superconductor. There's a coupling between the superconductors on the either side, and you basically can get a Cooper pair from one side goes through to the other side, through the insulator, and you get a dissipation-less transport. So it's not just simple tunneling, but it's transport involving Cooper pairs. It's a transfer of Cooper pairs, so it's a dissipation-less transport. So this was sort of the first, and you can actually derive this, the easiest and simplest way to think about is in the proof I've seen of Josephson physics is in Feynman lectures. You don't need to know the microscopic mechanism of superconductivity, but you can actually derive a lot of the properties. So this is one version. There are many kinds of Josephson junctions. You can also realize Josephson junctions by sandwiching a normal material, in this case graphene, in between a superconductor, and the net result is you get a transfer of Cooper pairs, except in this case, or in the case of a normal metal sandwich between superconductors, it's mediated by an Andreev reflection, and there's a bound state. So electron reflects off this interface between the superconductor and reflects back as a hole, and then that hole comes here, gets reflected back, and when they found a kind of bound state rather, you get a transfer of Cooper pairs, and that's basically the Josephson junctions. Okay, so these Josephson junctions, as I will explain a little later, they have lots of interesting properties which make them central to a lot of technological applications. I'm going to tell you about that in a little bit. So if you start with this simple picture without even knowing the details of what is a pairing, S wave, D wave, it doesn't really matter. You can derive sort of a relation. These are called the Josephson equation, that the current through this Josephson junction is proportional to the phase difference across phi1 minus phi2. This is one of the Josephson relations, and the other is that if the phase difference across this winds with time or changes with time, you start getting dissipation. In the absence of change in the phase difference with time, there is actually no dissipation. It's a dissipation-less transport. So the common ways one thinks about Josephson physics is there are sort of two kind of ways, which is DC Josephson effect, but it arrives from the same wholesome Josephson device. You measure the DC transport of the system, and you get a regime where there's dissipation-less regime, and then eventually it switches out of this dissipation regime into a dissipative state, and the Josephson junction is said to switch. Now, the other, which involves the change of phases, comes out of the same sort of device, but the easiest way to think about this system, and I won't go into a lot of the pedagogical gory details, but you can think of this Josephson device in terms of the phase difference. You can write this down as a kind of potential in this, not in real space, but phase, which is this phase difference across the Josephson junction. And when you apply a DC current through it, you actually tilt this potential. And the system lives with a fixed phase difference, but eventually it tilts so much that it starts running and you get dissipation. That's one way to think about this. But when you think about the dynamics of it, it's basically a particle sloshing around at one of the minima or going in and going to the other minima. And you can have a plasma frequency for this kind of a Josephson device. But at the heart of it, electrically, this device works like a nonlinear inductor. So normally everybody knows from basic electrical circuits that an inductor is basically geometry dependent number of turns and the properties of material that you have put in, permeability that come in. But this inductor using the Josephson device depends on actually what the current is. So it's an unusual kind of inductor. And we know other kinds of nonlinear devices like resistors, etc. So it's a very important, electrically an important thing. Now, this is sort of an introduction. Now, I want to address the question, why are they interesting? So these kind of Josephson junctions are now one of the key sort of, let's say, approaches to realizing qubits, transponds, and everything. The central idea is a Josephson junction with some additional, capacitive elements. You can make amplifiers, which I will show. So Josephson junctions are very critical. The metrology, which is basically measurements of quantities, the new system of SI units is based on the Josephson effect as one of the key nodes. And then there's a huge set of possibilities of making new kind of sensors which can sense a wide variety of things from photons to heat to spins and whatnot. So a lot of the work is going on in this area. So that's why these sort of basic motif of a Josephson junction is an important building block. So you might say, okay, everybody has been making these kind of Josephson junctions based on aluminum oxide based technology, which is sort of the most common platform. Why do something which is, or why try to fix something which is not broken? Turns out that you don't have to fix it, but you can bring some additional functionality which is not there in that architecture of aluminum. Sandwich with aluminum oxide is a very nice oxide, and then aluminum, and you get a tunnel-based Josephson junction. So you can bring new kind of functionality which is not available or not possible even in those kind of Josephson junction, and that's sort of why we, in my lab, we're spending a significant amount of effort to look at Josephson junctions in a wide variety of implementations. Okay, so that's sort of the rough place where we are now. I gave you a rough, sort of a basic introduction to Josephson devices and why they're interesting. Now I'm going to slowly segue into the first sort of experiment, which is a high temperature Josephson diode. So I want to start a little bit by talking about non-reciprocal transport. So what is non-reciprocal transport? We have already sort of familiar with non-reciprocal devices. There are many around us. The most common is a PN junction diode, where you apply a bias voltage of opposite sign. The electrical current that flows through the device is different. So it does not have reciprocity because the inversion symmetry of the device has been broken. Okay, that the left and the right are not the same. They are doped differently. Now, these devices arise from breaking of certain symmetries. So now people have been, over the last several years, have been thinking about devices which are superconducting analogs of this, which are broadly called superconducting diode. Of that, Josephson diode is a special kind of sub-creature, if you like. So this requires broken inversion symmetry and broken time reversal symmetry. Then you can actually realize a device which is non-reciprocal but in the superconducting state. Okay, so so it will switch at one current on one bias and a completely different bias value for the other direction. So it's interesting. So you can make, there's a interest and need in terms of some sort of applications to make non-reciprocal devices in superconducting systems. And in this case, you will have the two currents not being the same, the switching currents not being the same. So if you have been following this literature, there has been a lot of interest in trying to realize these kind of physics of diode effect over the last something like 5 years. There's been kind of very hectic activity. And people have basically broken inversion symmetry and time reversal symmetry in a lot of different systems by using a lot of different knobs. But the temperatures at which these devices work are millikelvin, and the asymmetry, which is the difference in the current that can flow in either of the directions, is relatively very small difference. So in our work that I will show you with BISCO, which is a high temperature superconductor, we can realize these kind of physics, and not just this. but more complex devices that I won't talk about today at liquid nitrogen temperatures. And that's sort of an interesting, opens up some possibilities. Okay, so let me briefly talk about the material. I won't go into a whole lot of detail, but one of the van der Waals material, which is not as much studied as graphene, is BISCO. This is the acronym, but this is 2212, and it has a TC of about 85 Kelvin. It's a ceramic which has these planes of bismuth oxygen, strontium oxygen, calcium. Then the key is this copper oxygen planes, where the superconductivity lives. And there are these layers of other copper oxide planes, and they are Josephson coupled. There's an intrinsic Josephson junction because effectively these layers act like tunnel barriers. And superconductivity is strictly 2D and couples across the layers, and the TC of 1 or 2 unit cells is also the same as bulk. Okay, so there is Josephson coupling, and the superconductivity living here, and it's a type 2 superconductor, but importantly it has a D wave order parameter, which makes interesting things fun, and also will show up in the experiments. So this is the phase diagram. Some things everybody agrees on in high TC superconductors is, but exactly the microscopic mechanism of high TC superconducting is an outstanding problem over the last several 30 or 40 years. I don't need to know, for understanding this talk, we don't need to know the details of it, so I'm going to kind of gloss over them. Yeah.
My question, what's the role of bismuth and strontium if everything is going on?
Yeah, so they're charge reservoirs, they put electrons into the copper oxygen planes. But effectively, I'm going to simplify it for the purpose of this talk, but they act like tunnel barriers for the rest of the physics. Okay, so there's a D wave symmetry of the order parameter. This is completely different from aluminum or other wholesome superconductors that you may love. And that makes it sort of fun to do physics with. So around 2021, there was a lot of interest in people who were twisting whatever they could lay their hands on. So people said, why not explore BISCO? So there was this work which basically theoretically proposed that if you twist 2 layers of copper oxide plane or BISCO, by 45 degrees, then you could get some interesting physics. Namely, their key prediction is that when you twist it by 45 degrees, you get a kind of a topological superconductor, which breaks time reversal symmetry, and it's like a D plus ID kind of superconductivity at the interface when you twist it. And the idea is that there is a co-tunneling of Cooper pairs across the superconductor. Okay, so this sort of was certainly very attractive, that you can have topological superconductivity at temperatures like 50 Kelvin, which is unheard of. So a lot of people got interested in it. But one of the challenges in this material is that it's extremely difficult to work with. You exfoliate it and you leave it for a couple of hours, it's actually degraded because the oxygen in BISCO is metastable. So you get off stoichiometric stuff very quickly. And that's why there are not many people. Yeah, so their proposal is that when you have these co-tunneling of Cooper pairs, then you can get these 2 possible states, which is circulating in one way or another at the interface. So it's an interfacial superconductor with time reversal symmetry broken. Okay, so that sort of got us also interested, and a few people, I think one of the few people to start is working on this very early on BISCO was Philip Kim's group at Harvard. So to make these devices, it's a little bit complicated. You have to peel off and exfoliate at low temperatures to make sure that the oxygen stoichiometry does not get distorted. So you take a crystal of BISCO, exfoliate while the sample is still below -100 C inside a glove box. within a minute or so, you twist it by whatever angle you want and you put it back. It does not like any kind of lithographic processes that people use for making electrodes. You have to make electrodes by shadow mask. If these words mean anything to you and you have questions, please talk to me at the coffee time, but some of this is technical fab related jargon. So at the end of it, it's the same flake. You peel off, same mother flake, and you peel off and you place it back. And this is the region where the Josephson junction is formed by putting it back. And these are the many electrical connections that we need to make the measurements. Okay, so this is sort of the cartoon of this device. So it's not monolayer because working with monolayer, while we make them, these kind of sort of gymnastics with cutting, peeling, putting back makes the yield especially low if you work with monolayer. For the interfacial Josephson junction, it doesn't matter whether it's a few nanometers or a unit cell. So we work with about 10 nanometer thick flakes. So we make these kind of devices and we started measuring these response of this device. And what we see is that the switching current of these two sides is different. Okay, and this is at 30 Kelvin. You'll also see a magnetic field being applied to it, and I'll talk about it later. So these are Josephson junctions because what's happening is that you have one superconductor and a kind of a twisted insulator, and there's one order parameter, and the order parameter of the lower one is rotated by whatever is the angle of twist. So it's a Josephson junction, and Josephson junctions themselves are stochastic devices that if you take an aluminum Josephson junction and you switch it many, many times, it will not switch at the same current. That is not a bug of the device, it's the feature of the device because it's actually, a system lives in a well and you run it out by tilting the washboard potential. So when you switch it many, many times, this is some 10,000 switching events, you see that there are some multi sort of humps in this, but that's related to the physics of high TC. I won't go into too much detail here, but I can talk later. But they are asymmetric. So this is sort of what is called the Josephson diode. There are similar results from Philip Kim's group, which explored some other physics. This was published a month before our work. Yeah. Yes, we made those also. I'll talk about it a little bit, but not a whole lot because of time. But those are sort of control devices. They have so when we peel it off and put it back, we can put it back with an accuracy of about, for this stacking setup inside the glove box, we have an accuracy of about 0.3 or 0.4 degrees. So they show small asymmetry, but they do show asymmetry. Not as much as the 45-degree twisted device. So this is the Josephson junction, the purple colored artificial Josephson junction, and you have these intrinsic Josephson junctions, and we can measure these by applying a perpendicular magnetic field. Okay, and what we see is that asymmetry in these, which is characterized by this parameter, is tunable with magnetic field, but it's actually tunable with a very small magnetic field. Earth's magnetic field is in this range somewhere. So we had to build a special setup to shield out a cryoperm box inside to shield out Earth's magnetic field and then have an electromagnet inside to generate the magnetic field. So this asymmetry can be tuned with a current, and it has some small hysteresis due to magnetic field, and it goes up to about 70 Kelvin. And there's an overall symmetry of the problem, not just in terms of the asymmetry, but in the switching distribution. So the switching distribution of plus side and minus side is different, which is kind of central to why this device works as a diode, and I'll talk about it. But when you flip both the current and the magnetic field, you get the same thing, which is required. If the system breaks this kind of symmetry, then there is some problem in the experiment. So this magnetic field actually corresponds to a few quanta of flux through this Josephson junction, order of 1 or 2 or 3 quanta flux that can tune the polarity of this Josephson device. Okay, so largely the largest asymmetry is for 45 degrees, and for controls that we did, the asymmetry reduces as a function of temperature, but is the smallest for largest for 45 degrees and small for very small for other angles. So we spent quite a bit of time trying to think about the mechanism, and the mechanism of this this work relies on two kind of perspectives which are complementary. Is in high TC superconductors, there are two kinds of vortices. One is Josephson vortices, which live between the planes of copper oxide, and vortices which are perpendicular to the copper oxide planes, which are called the pancake vortices. And when you twist, you are actually reducing the Josephson energy, because as you twist the two layers, the critical current or the switching current reduces because of the D wave order parameter. Now, the Josephson energy gets reduced as a result. When you have two pieces of the pancake stack, you can, in between this artificial Josephson junction, you can have a Josephson vortex, which when it starts to move or slide, you get dissipation. Okay, so that's sort of the real space picture of thinking about why you have a diode-like effect. A kind of a phase picture of thinking about this Josephson junctions is that if you have a current phase relationship which has higher order components, so it's not just I proportional to sine phi, but some other terms like sine 2 phi or even higher order, your current phase relationship or the potential rather will have these kind of other higher harmonics. And if you look at this kind of cartoonish picture here, if your system lives here, the barrier for it to overcome this potential is different from the other, and that's why you see this asymmetry or the diode-like response. And this also explains why the switching distribution on positive current and the negative current is vastly different, because the barrier that it sees is very different from two sides. Okay. There are lots of subtle issues, some we don't understand, and some more gory details which are in this paper. So you're welcome to take a look or talk to me. I'm happy to tell you exactly what we know and what we don't know. Okay, so what we are doing more with these devices, we've already implemented sort of squids based on two twisted Josephson junctions in parallel in a loop, these kind of squid-like devices have interesting implications. Among many theoretical predictions that are out there, I think there was a speaker here who in his talk talked about, I think was involved in work related to some sort of qubit proposals in using D-wave symmetry, which have also come forth. These are a little bit challenging, but they may lead to some other interesting physics, and we are kind of looking in that direction already. So I told you about this. In the next 12 minutes or so, I'm going to talk about this other story, which involves the central character is still the Josephson junction, but used in a different way completely, or in a different platform. Okay, so let me give a preface to this, is that whenever we want to transduct or measure signals out of any quantum device, like a qubit or any other system, the power that's coming out of these systems is very small. It's a fraction of a femtowatt. But eventually, you have a processor in the dilution fridge, but eventually you want to measure signals come to room temperature, the power has to be much large for the electronics to deal with it. So you need amplifiers which will amplify the signal over many, many orders, orders of magnitude. And so you need an amplifier. An amplifier invariably amplifies the signal, but also adds a noise of its own. So you cannot have noiseless amplification. You can minimize the noise, and the device that I will show you does precisely that. It adds noise which is at the fundamental limit, the least amount of noise allowed by quantum mechanics. So why should one make this kind of amplifier? The easiest way to think about it is that one amplifier doesn't amplify from here to here. You need like 3 or 4 amplifiers at different stage of your measurement scheme. So each one of its amplifiers adds noise, then this guy amplifies this noise, and so on. So eventually, the overall gain of the chain of these amplifiers is the product of the gains. But The added noise, which is characterized in terms of a noise temperature, which is not necessarily the temperature at which the amplifier lives, but it's a characteristic amplitude of noise, it adds in a weird way. So the first amplifier's noise temperature cannot be reduced further, whereas the other noise contributions can be sort of de-amplified or de-emphasized because of the gain of other amplifiers. Okay, so this first amplifier has to add the least amount of noise, and that's why one needs amplifiers or ways to sort of transduct or improve your signal, which is sort of adding a least amount of internal noise to it. And that's sort of what we did. So what we do is we use Josephson junctions, which I showed you earlier, which is how this looks. And if you look at the differential equation that explains the physics, it's basically can be written down. This is just summing up of the Kirchhoff's current across these three. This is the current through the Josephson junction. And instead of now writing in terms of voltage and everything, you can rewrite it in terms of phase. And this becomes a second order differential equation, okay? And if you assume that the current phase relationship is like this, you can keep the leading order terms, and it has this phi of t and some higher cubic term, which makes the oscillator unharmonic. If it's just phi t, then you have a damped harmonic oscillator, but if you keep higher order terms, it's an unharmonic oscillator, and that's kind of important. And when you have an oscillator like this, a damped harmonic oscillator, the way to think about how this amplifier works using the Josephson junction is to think of a spring constant, or as I'll show in a picture, a spring constant which modulates with time. So parametrically modulated spring constant. So you have a knob, external knob, where the spring constant of the material changes. That's basically this equation which describes that. So it's called a parametric damped harmonic oscillator. And when you do that, you basically have a solution where you counteract the damping by this amplitude of this parametric drive. So it's sort of counteracting. Damping is a route towards amplification, and that's sort of at the heart of how this device works. So if you have been on a swing and without anybody pushing from outside, and you increase your amplitude in a swing, that's basically a parametric process by which you have increased your amplitude. So that's basically this physics in action. And this is very general. It's used in optics and a lot of different fields, and people have used it in RF electronics as well. And we used this idea in this using the Josephson junction. The Josephson junction based circuit acts like a nonlinear medium. And this is sort of the one takeaway slide, if you like. So you have a nonlinear oscillator. So when you drive it at large amplitudes, you reach a point, which is this orange curve, where this is extremely sharp. At that point, you get amplification. And this Josephson junction shunted by a capacitor is also an oscillator, LC oscillator, which is exactly a harmonic oscillator state. It has this quantum harmonic oscillator. It may be unharmonic, but it has these level spacing. And we work at temperatures where kBt is much smaller than this level spacing h cross omega. So typically this resonator that I'll show you, they work at about 5 to 6 gigahertz. And at 15 millikelvin is much smaller than h cross 6 gigahertz. And you combine together, you get amplification, and the amplification with noise, which is quantum noise limited. Okay, so this is the noise temperature of this system is not 10 millikelvin, but effectively h cross omega by 2 kb, because the noise that is added is this 0-point fluctuation of this quantum harmonic oscillator. This is h cross omega plus half times n. So even if it's in n equals 0, there is this quantum fluctuation that adds noise. So there is a need to make new kind of devices away from aluminum oxide, which is sort of the platform with which people make these kind of amplifiers routinely now. You want to operate at high magnetic fields. You want to tune not with flux, but with an electrostatic gate. And you want to make new kind of sensors. And that's sort of what motivated us to make this using graphene. Okay, so there has been a lot of work over the last 10 years on different kind of realizations of graphene Josephson junction. So what you do is you take graphene, you contact it with a superconductor, And if it has good transparency, you get these Andreev bound states and you get a Josephson junction. So this was one of the, not the first, but one of the nicer Josephson junctions formed by sandwiching graphene with boron nitride. And the current phase relationship is a little bit more complicated. It's not just sine phi, but some other terms involving the transparency, but it doesn't affect any of what our goals are. So the basic circuit that I'll show we make is this L from the Josephson junction and a capacitor. You shunt it and you make a oscillator, except that it's unharmonic, so the levels are not the equispaced, and that's sort of the starting point. So people have made different kinds of devices using Josephson tunable resonators, even qubits, transbound qubit using graphene Josephson junction, which is not very good in terms of its coherence, and then sensors. So we sort of decided to go down this way and realize amplifiers because we wanted to make new kind of sensors as well. So this is sort of what our device looks like. This is a scale bar. This is 10 microns. 100 microns. 100 microns is typical diameter of human hair. This is a cartoon. So this is where the Josephson junction is. These are lines, RF lines to guide the gigahertz photons into the amplifier. In reality, this part looks like this. You have these capacitors. You have a graphene Josephson junction, graphene sandwich between boron nitride. These are superconductors. This sort of orangish material is a superconductor called molybdenum rhenium. And there is a local gate underneath it which tunes the density of charge carriers in graphene. If these two fingers of the superconductor across which the Josephson junction is formed is separated by about 300 nanometers or less. So, and the gate underneath tunes the density of charge carriers. So in the cross section, it looks like this. The supercurrent flows in this graphene layer. Okay. So what we have is an effective circuit which looks like this. You have an L of the Josephson junction and you have a capacitor. Yeah.
How good is the contact of Mori to graphene?
It's one of the best you can get. It makes very low resistance contacts. But transparency is a slightly different beast than resistance. So even you could have the same resistance Josephson junction, but the transparency is not good. So you won't get the Josephson physics, but it makes, there's a Wurth function matching between molybdenum rhenium and graphene. It gives the lowest contact resistance. Okay, so we basically want to get to this circuit by this device. And so this is the response of the device. By measuring, sending gigahertz radiation and measuring the phase of the signal change as it reflects off the device. So through these sort of waveguides, we are shining our gigahertz radiation and looking at the reflected sort of radiation, gigahertz photons, if you like, and change of phase. This is a very, measuring phase is much more sensitive way of measuring the performance of the device rather than amplitude, because this device will not have any change in the amplitude because it's actually a perfectly reflecting device. So this line is the tuning of the resonant frequency as a function of gate. So you have a capacitor which is fixed, but you have an inductor which is now tunable with gate. So you basically get a tuning of the resonant frequency with gate. So you can tune its resonant frequency from 6 to 2 gigahertz. Okay. So typical Josephson junction, to tune, you have to apply magnetic flux. Here you don't have to apply magnetic field at all. You just dial in a voltage. That's sort of the nice bit. And if you can have a bandwidth of tuning of about 3.5 gigahertz. So when you have this device, you have to make it nonlinear, because if you have just a simple, sine phi has this term phi and then phi cube. If you don't have higher order terms, you actually don't get any amplification. So you first have to make it nonlinear. So you have another gigahertz photons, which is called the pump photons, which essentially drive the system at large amplitude so that it samples the unharmonicity of the system. And if you sit at a particular gate voltage, as you increase the pump power, you will see that it bends to the left. And that's basically because this cubic term is kind of softening or reducing the frequency. And when you reach here, way beyond, you go into sort of an unstable state of the amplifier. But right here it provides the largest gain. And so that's where we sit. And we look at and we add a signal that we want to amplify. And we measure the gain, which is what's the amplitude before and after, and sort of look at the ratio and plot it on a logarithmic scale, and we see it gives a gain of about 23, 24 dB, and which is comparable to the best discrete parametric amplifiers. And what is important is this kind of added noise, which is the noise that the amplifier adds, and that's this red dots. And the green dashed line is h cross omega by 2 kb, which is the quantum noise limit. So it's right at the quantum noise limit with a noise temperature of about 200 millikelvin. There are lots of interesting possibilities to take this further just in terms of amplification, but in terms of different kinds of sensors. So I pretty much finished talking about what I promised. I maybe take a minute to show how you can make new kind of sensors. This is somewhat new and unpublished stuff. So you can make these kind of Josephson devices as sensors. So people have been trying to make bolometers. So bolometers are basically devices which measure radiation or energy landing on them by different methods, different principles. And graphene is particularly interesting because it has a very low electronic specific heat. And the electron-phonon coupling is very poor at low temperatures. So if you dump energy into the electrons, they remain hot. And if you have some mechanism to sense that hot electrons, you have an exquisite sensor. And that's where these bolometers kind of come in. So the architecture that we use is, this phase of this resonator it reflects the Josephson junction's inductance. So if now some photons land on it, it will shift to, because the Josephson junction's properties are changing. And we measure that, and it basically becomes, we have shown that it becomes a very sensitive bolometer. And these are those kind of devices where the graphene is a bus, which is the same graphene that forms the Josephson junction, also collects any photons which are landing on it or any heat, and carries it to the Josephson junction, and the Josephson junction faithfully senses whatever has landed on graphene. That's basically all. I have some details, but I think let me just stop and not take more time. If there are questions, then I can sort of talk more about how it's done, about the bolometer, and but this is what I promised, and I'll stop here. Thank you very much for your kind attention.
Thank you very much, Mandar, for a great talk. Any questions?
Yeah, hi, thanks for the nice talk. So in the first part of your talk, in the twisted Josephson junctions, you applied a magnetic field. So is it a minimum requirement, or you wanted to have the tunability? Because your time reversal symmetry was...
Okay, thanks for that question. So we were, looking for tunability. And in our experiments, we don't have a smoking gun evidence of a time reversal symmetry broken superconducting state at the interface. So Philip Kim has done more experiments, additional experiments, and from measuring Shapiro steps, they see some higher order terms in the current phase relationship, and they say that that's evidence. You should look at their paper, but briefly. So they say that they have evidence for a time reversal symmetry broken superconductor. We are doing some more experiments to try to find more direct evidence for broken time reversal symmetry. Right now, our experiments, we don't have an evidence for time reversal symmetry broken superconductor.
I was just wondering, since you use the BISCO what is the TC for the interfacial superconductivity?
It's very close to bulk, so you have to work very hard. So it's we have devices which work up to 80 Kelvin. We have squids which work at 80 Kelvin.
So the devices you are making out of this, so they are expected to really work high temperature.
Yeah, I mean, if they don't, then there is no fun.
So of course, BISCO is known for its cleavability, a very good cleavability, and you used single layer BISCO or
No,
that was
for none of these experiments that I talked about, we don't use single layer or single unit cell BISCO. It's about, unit cell is about 3 nanometers thick. We use about 10 nanometers. Primarily to, we do very fast to reduce this degradation, but it's, the degradation is happening. Because you make it, even you do it in glove box, you have to put it in a cryostat. So you need some reasonable amount of time.
I didn't mean really that. Like for the BISCO, you know, you can go from single copper oxygen layer in the unit cell to 2 layer, to 3 layer.
That's right.
And TC keeps on increasing.
No, so not our experiment. There is an experiment which has shown directly with single copper oxide plane. The TC is that of bulk.
I see.
And we also don't see any systematic TC dependence with the thickness.
But you never did any BISCO experiment where there are 2 layers in the unit cell itself. I think there is.
No, we have not done it, but others who have it by exfoliation, not by growth.
No, not by exfoliation.
The question is that there are actual bulk system, which is not BISCO, derived from BISCO.
Okay. Not 2212, but others.
Yeah, the higher order.
Okay, now I understand. Thank you for clarifying.
You need a chemist.
No, yeah, so no, we have not done. We have thought about it, but there are already so many other things to do with this. But you're right, we have not done that. Yeah.
Just, I'm curious, the fact that you have series of Josephson junctions on each side and then rotate.
Yeah.
Does that have any implication?
Yeah, thanks for that question. So you have Josephson junction, which are the intrinsic Josephson junction. Their switching currents are much larger than the one which is twisted because this guy is sort of the weakest link. So when you send current through it, the weakest link pops out first, and then at higher currents, so we can see the difference between them. When we make 0-degree control experiments to prove people that we have good Josephson junctions, we made 0-degree, the critical currents or the switching current densities are comparable to the bulk ones. So the interface is not getting degraded.
That kind of control on the rotation, because I would expect that whatever you do, bringing back mechanically another layer, there would be some angle.
It's because you're using essentially a gear mechanism. That's sort of, for example, for graphene experiments, you do 1.01. So you have a very precise gear mechanism to dial in the twist. So getting 0.01 degree rotator is not, you just need money in your pocket. That's all.
Well,
So you can buy off the shelf a motorized rotator, which will give you an accuracy of 0.0005 degrees.
Just a quick follow-up, like what's the difference in critical current? Like you said, the twisted one, the weakest link.
So it's a function of angle. So as you twist 45 degree, the switching current density is the least, and as you go larger, the critical current density, it will basically, we have it in our paper also, but there are other groups who have a lot more manpower. So they have mapped out the JC as a function of theta, and it shows minima at 45 degrees. It's not zero. You will see data which shows scatter here. So it reduces as a function of the twist angle.
So do you see, it's a low dimensional superconductor, right? So
Sorry?
do you see phase slip events in the IV?
Of just simple BISCO? Sure.
You twisted, like, do you observe?
Yeah.
Because in IV traces, I have not seen any jumps.
At large currents, you do see phase slips. This is not sort of we have done some work earlier.
Okay.
You can look at it.
Okay.
So, I mean, it's not surprising that it would happen because it's simple superconducting physics.
No, so Mandar, what stopped you from doing the Shapiro steps in the first part?
No, nothing stopped us. I don't think personally it's a way to measure the current phase relationship, but there are ways to measure the current phase relationship directly, which is what we are doing. Shapiro steps is one way to show that you have higher order harmonic components. That's all. So it's not measurement of the current phase relationship. It's
You just didn't do it, is that?
no, we were, let's say, we were actually more interested in trying to directly measure the current phase, which is still our interest. Because the Shapiro steps measurement is not a smoking gun evidence. It's indirect some sort of statement that there could be some higher order components.
I have a last question, it's technical. When you showed your device, there was this 4-point contact in which there's a Josephson junction as well as there is a part of BISCO itself involved. So what steps do you follow to separate out the contribution of the Josephson diode effect and superconducting diode effect?
Yeah. So this is kind of important. So one of the things we wanted to ensure at each step in our fabrication, we measure electrical property of this flake to always check that this is itself not got degraded. You know, these set of electrodes here, you send the same current through, which goes through the Josephson junction and the two flakes, and you check the health of these two guys. These electrodes, it tells you about this, but if you measure this guy and the other one, then it tells you expressly about the Josephson junction. It will
have BISCO.
Yeah, it has some BISCO for sure, but as I told you, the critical current of the BISCO which is flowing in plane is much larger than that of the Josephson junction, which is the weakest link. So you see that one, any feature that shows up as you switch it will be from that Josephson junction. How do you see?
Someone has a question online. Why current in JJ always changes? Yeah, Josephson junction.
Well, it can, as long as the current phase relationship can be maintained, the phase will adjust the phase difference phi1 minus phi2 to ensure that the current flows. And the current will flow without any dissipation. I don't know if that answers the question. I mean, if you have a question, please email me if I didn't answer.
Anyone in the hall has any further questions?
Yeah, so I had a question from the second part of your talk. What determines exactly the noise temperature of this kind of a Josephson parametric amplifier?
Yeah, so thanks for asking that question. It gives me an opportunity to re-emphasize this part. So the amplification relies on the nonlinear second order harmonic damped harmonic oscillator, which is, if it's a completely linear kind of a resonator, the response is Lorentzian, this blue curve. But as you make it nonlinear at large powers, it tilts to one side. So that's the gain part. The noise that is being added by there are lots of sophisticated ways to explain it, but the noise that is added is from the physical device. It sits in the ground state at 15 millikelvin. And if you look at the anharmonic oscillator, you have these anharmonic levels. Each one of them are separated by something like h cross omega. Even if you say they're anharmonic, they're order of h cross omega. Now this guy has this 0-point fluctuation of the harmonic oscillator. That's the only source of noise it has. So the noise is h cross omega by 2, which is converted to temperature because it divided by kb, and that's the noise temperature. So that's the only source of noise in this amplifier.
So it doesn't depend on the material properties or anything like that?
No, that is the beauty of it, in the sense that it's based on the Josephson physics. It doesn't care whether it's made out of aluminum or made out of graphene, Josephson junction, or anything else. It depends on this sort of harmonic oscillator level spacing.
Thank you.
Yeah.
Is the diodic behavior maximum for 10 nanometer thickness? Or how does it change if you change the thickness of the flake?
So in our pretty fat supplementary information, you will find lots of these other control devices of different thicknesses. So it doesn't really have much of a thickness dependence. The way of making these devices is that, because you peel it off, one of the drawback of this cryogenic explosion is we don't have very good control over what thickness is upper layer and lower layer. We take a flake, we peel it off. If it gets cleaved off, then you put it back and then finish measuring after the measurements are over for while then we do the AFM. So we don't have very deterministic control to say, okay, I make the upper layer 10, lower one 5, then so right now we are not at that stage to deterministically make different thicknesses. So far what experiments we have done, we don't see any thickness dependence. It's just the interfacial Josephson junction. So zeroth order doesn't care about the thickness of the superconductor.
And regarding the second part of your talk, so does the gain change with the gate voltage you apply in graphene?
Good question. Yeah, so the gain itself doesn't change. In fact, the noise temperature also varies a little bit, but it doesn't change a whole lot. Something else that happens, which is device specific, is that when you tune the gate voltage, when you have this gigahertz photons coming in, it wants everything to be 50 ohm impedance. If it deviates from 50 ohm, then there can be reflections that can happen, and that can kind of distort the gain that the amplifier is giving. The physics of the Josephson physics, but it's the fact that the path of the gigahertz photon is no longer 50 ohms, and it's that which causes degradation. Again, that's some fair bit of data in the supplementary information.
Okay, thank you.
Okay, maybe we can catch him. Any more question, please feel free to catch him over coffee. Let's thank the speaker for this great talk.